Ono and his colleagues then analyzed the data that they'd collected from their live occupant low-speed test collisions. They found that the combination of compressive force and shear force altered the way that the vertebra moved in relation to one another. They first started with established knowledge of how the cervical vertebra move. Previous research had shown that each vertebra rotates around the one below, like this. This point of rotation is referred to in the biomechanical literature as the instantaneous axis of rotation, or IAR, and permits the smooth gliding motion of the facet joints. Ono et al. Then compared this normal rotation with the motion they observed during rear-end impacts and found that the point of rotation, or the IAR, actually moved during a crash. Instead of this motion, they found this motion. These findings prompted Ono and his colleagues to write, "This is a non-physiological motion of the vertebral segments." In summary, they saw that the spine was subjected to rapid compression, then shear, which caused abnormal motion in the facet joint, all from a collision of just 5 miles per hour. Shortly after this research was published, other research teams from the Yale School of Medicine and Wayne State University reported similar findings. A study conducted by Grauer et al. Was studying the problem of spinal motion at the same time. They examined the degree of rotation between each of the different vertebrae in the spine in a set of simulated car crashes in cadavers. They first measured the normal range of motion that each joint could handle, and then subjected the specimens to impacts of 2.5, 4.5, 6.5, and 8.5 Gs, similar to what an occupant would experience in a low-speed crash. Grauer found that the joints at C3, C4, C6, C7, and C7, T1 moved less than 5 degrees during normal extension. When the spine was subjected to greater impacts, the C6, C7, and C7, T1 joints experienced dramatically greater rotations than they could handle, while the C3, C4 joint stayed within its physiological range. Another team of researchers from Wayne State University was also studying the problem and performed some different experiments with cadaver spines. They found that the cervical spine does not handle the combination of compression and shear well at all. In fact, they found that the ligaments that hold the spine together weaken dramatically when compressed. As this graph shows, they found that the lower spine lost as much as 70% of its resistance to shear when it was compressed just 40 pounds. 40 pounds of force may seem extreme, but the study by Ono et al. Reported compression of 56 pounds in a collision of just 5 miles per hour. The final piece of the puzzle was discovered by another team of researchers who published their findings in 1999. These scientists decided to study in detail the motions of the facet joints during a rear-end collision. They carefully prepared a cadaver spine with special reflectors placed on each cervical facet joint. They then subjected the spine to an impact approximately equal to a collision of about 4.4 Gs, or what would be experienced during a low-speed crash, and recorded the motion with high-speed video. They found that the facet did indeed experience the abnormal motion that was seen by the other researchers. Instead of gliding smoothly across each other, as facets do in normal motion, the upper facet joint rotated abnormally and pinched the lower joint. Furthermore, these researchers found excessive flexion in the upper spine during the S-shaped portion of the whiplash motion. The authors of this study concluded, excessive stretching of the posterior upper cervical complex and the pinching mechanism due to compression and sliding of the facet joint may explain the presence of suboccipital headache and neck pain, respectively, in patients with whiplash-associated disorders.